Good morning, everybody. This is an A7 practice test, and I figured I'd go ahead and mix things up a little bit by putting some Tesla questions in here. I could build a test on all of the older stuff, which is basically kind of what I covered on the previous video that really didn't get all that many views, not like a lot of them do. But this is an advanced test. If I made any mistakes on the Tesla R1234 part of it, feel free to let me know. I'm not that easily offended. I had one guy that saw my cylinder pressure rundown test, videos. People are still watching that thing, and some people will write long replies to tell me everything that I said that was wrong or whatever. That's okay, I'm not too bothered about that. I don't typically put up with nasty, ugly comments, but if somebody has got constructive criticism, I take it. But here's their first one. Which of the following is a primary technical characteristic of R1234YF compared to R134A? Does it utilize a significantly higher operating pressure range? Is it classified as a mildly flammable A2L refrigerant? Is it fully compatible with standard mineral-based oils? Or does it eliminate the need for a dedicated refrigerant identifier? It's classified as a mildly flammable A2L refrigerant. I had a refrigerant identifier not long before. Peter Call had sent me one that I got from him that would do 1234, but it also did the others, from Neutronics. So you don't have to have a dedicated refrigerant identifier to that. But typically, most of your R1234 machines, the newer ones, will have a built-in refrigerant identifier anyway. And so you don't usually need a standalone refrigerant identifier with all that. All right. Question 2. All of the following are required when servicing R1234YF AC systems except A, an SAE J2843 certified recovery and recharging equipment. B, a integrated or standalone refrigerant type analyzer. C, a standard 134A manifold gauge set with adapters. Or D, unique service couplers designed for R1234YF ports. You're supposed to not be able to use an R1234. You got to remember, a lot of these questions have got except, you're picking out the only wrong answer, so be aware of that. That you're not supposed to use standard 1234 gauges, although a lot of people get adapters and use them anyway. Well, the concern is cross-contamination, obviously, and so, take that for what it's worth. If you have to, take your ESCO test, you might think about that. Question 3. In a Tesla vehicle equipped with a heat pump, the octo valve is used to what? Regulate the flow of high-pressure liquid refrigerant, direct coolant between the battery and the drive units, control the speed of the electric AC compressor, or adjust the blend door position for cabin temperature. You might have seen there's several different versions of this valve, earlier and later and all that kind of thing. It directs coolant between the battery and drive units, and you can see here this little, pause long enough to read this little description here. But it's actually going to switch the flow of the coolant to where it's needed, because it's keeping up with all of that. The batteries are swimming in coolant. The whole underside of the car is the battery, and the coolant's in there. The bad thing about that is, in my estimation, you run over something that knocks a hole in that, you're going to lose your coolant, and then you could have a runaway fire on your hands that the fire department's going to have a lot of trouble putting out. They need to come up with some way to put those fires out on these Teslas without, if they get a big crane with a dome to set over it or something, so it shuts off anything. I don't know. That's just crazy what they're doing here with them fires. Question 4. A vehicle with an R1234YF system has poor cooling. Which of these is the least likely cause? Remember, we're looking for the wrong answer. Mixing R134A refrigerant into the R1234 system using a PAG lubricant not formulated for 1234YF, a restriction within the liquid line or expansion valve, or the presence of a small amount of UV detection dye. Typically, you can put a little bit of dye in here. It's not going to hurt anything, but you mix refrigerants or use incompatible oil, so on and so forth. You can see all of these other answers and why they're right, and this one here is wrong for this question here. This is the least likely cause just because you put some detection dye in there. Now, if you put, that's the reason it says small amount. If you put a lot of dye in there and it's the wrong, it's mixed with the wrong kind of oil, it can eat the insulation off of the wires in the electric compressor and cause it to melt down, burn up, whatever. Question 5, regarding Tesla's heat pump system, which of the following statements is false? Remember, we're looking for the wrong answer here. A, it can scavenge heat from the battery and drive unit motors. B, it uses super manifold to house various thermal components. C, it relies on a high voltage positive temperature coefficient heater as primary heat source. Or D, it's designed to be more efficient than resistance only heating. It relies on this heater as the primary heat source. They don't want to use battery power if they can get out of it. You want to extend your range. You don't want to be chewing up battery power when you're on a trip or you're sitting beside the road because you're in a traffic jam somewhere on an interstate. That's just not a plan. Question 6, in a typical automotive AC system, the refrigerant is in what state at the evaporator outlet? High pressure liquid, low pressure vapor, or high pressure vapor? This being the evaporator, that being the evaporator outlet. This is the accumulator. Those parts. It's low pressure vapor. It passes through the evaporator, absorbs heat, prevents slugging. Remember, I told you it needs to be cold. It needs to be cold all the way to the compressor. Now it's flowing this way. Discharge line is here, goes through the condenser, dumps the heat it picked up in the evaporator, goes through the receiver dryer. This is a thermal expansion valve system, so it's got a receiver dryer instead of an accumulator. And then it comes back through the expansion valve where it's throttled as it goes through the evaporator. This gets too cold, it shuts that, it throttles that refrigerant, so there's not as much going through there. But it ought to be 100% low pressure vapor. If you have got any kind of liquid here that's leaving the evaporator going toward the compressor, it's going to cause big problems in the compressor. Matter of fact, Ford has got a strategy that they used on some of their vehicles called CASS, that's compressor anti-slugging strategy. If the compressor is mounted low so that the oil is puddled in there, it actually engages the compressor clutch while you're spinning the engine over to start it up, to start those pistons moving and get rid of any oil that might be in there, so it doesn't click on all of a sudden whenever the cylinders have got maybe some oil in there. They don't know when it's slugged. So that's something that a lot of people don't even know about, but if you look it up, CASS, compressor anti-slugging strategy, I think they call it, and that's a Ford thing. Other manufacturers may use it too. Question 7, a technician notes insufficient cabin heating in a Tesla Model Y. Which of the following is not a potential cause? Maybe an internal failure or blockage of the octovalve assembly, air pockets trapped within the glycol-based coolant loop, a restricted heat exchanger within the super manifold unit, or an overcharge of refrigerant in the high side liquid line. This is the one that's not a potential cause. Overcharge may affect cooling. It's least likely to stop the heating process compared to coolant side heaters. You see, we're talking about cabin heat, not air conditioning here. So if the octovalve, you can read these words. I'm not going to read all those words, so you can read that stuff. Pause the slide or whatever. Question 8, the coefficient of performance in an EV heat pump system is a ratio that A, compares the heat energy moved to the electrical energy used, B, measures the total displacement of the electric compressor, C, determines the resistance of the cabin blower motor circuit, or D, calculates the pressure drop across the internal condenser. It compares the heat energy moved to the electrical energy used. And see, this is a measure of efficiency you're not going to see on anything except an electric vehicle. So you probably have not heard of the coefficient of performance ratio. So you can read those words down at the bottom right too. Question 9. Which of the following is a key difference between R1234YF and R134A systems? An R1234YF requires a special moisture-resistant lubricant. R1234YF systems do not utilize a cabin-mounted evaporator. R1234YF is pressurized to 500 psi during static rest periods, or R1234YF uses threaded fittings instead of quick connects. It requires a special moisture-resistant lubricant, and so you can read the words there. Now let me zoom in on this picture right here. You've never seen this illustration before. You're not going to find it anywhere else online because I created it yesterday. If you see any mistakes in it, let me know. We're going to zoom in on it, let you have a look at it right here. That's your R1234 side, that's your R134A side. And so you've got some nice little stuff down here you can look at. You might notice in these drawings the absence of a receiver dryer. The reason the receiver dryer is absent is because it's built into the end of the condenser, because that's actually a subcooler. And so whenever the refrigerant goes from the discharge line into the subcooler, it goes through this dryer, and then it goes through the lower part, which is separate from the upper part, and that cools the liquid refrigerant off before it sends it back through the expansion valve to the evaporator. Now I should have made this line here a little fatter, because the suction line is going to be fatter and bigger than the liquid line, which is going to be a skinny little line. And you know, this chemical, you know, if that's wrong, let me know about that too. And here's your R1234 system. Look at the atmospheric lifetime, 13.4 years. That's how long it stays in the air. Not that that's a big deal, but they tried to make it a big deal. I had mentioned Ward Atkinson's name. He's an SAE engineer that's well known in the HVAC circles, you know, Mobile Air Conditioning Society and all that. I don't know if he's still living or not. He's an older man. And didn't even know he knew who I was. Well, I was at a MAC convention, and I was walking along, you know, where they have this ice sculpture in the middle of the room and tables around there where you've got these stand-up talking tables where you eat carrots and roast beef, you know, that they carve in the corners of the room. And I went walking by, and he got up and started pouring into my ear about ban the can and all this, and we're going to destroy the planet by letting the refrigerant leak out of these cars. And he was just really in my face, you know, wanting me to absorb all of this information and write about it in a magazine, I guess. I didn't even know he knew who I was. But when he saw me come walking along there, he jumped up from this table of bigwigs he was talking to and started talking to me about this. But the atmospheric lifetime of R1234, when it leaks out, it's only 11 days. You don't want it to leak out because it's so doggone expensive. You know, this right here, you know, didn't used to cost very much of anything at all. This right here is pretty dadgum high. But you can see these differences here. And like I say, if you see any errors in here, just let me know where I went wrong or something like that. You notice this says a heat exchanger that actually had both of the suction and liquid lines go through. The suction line, when it's on the way to the compressor, absorbs some heat from the liquid line so that it cools it off. Of course, your subcooler has already done that, but they wanted to run this through, and they did that. They came up with that because R1234 does not work quite as well as R134A. But the caveat is not all the 1234 systems have this internal heat exchanger. They just don't. So just don't expect to see one of these on every 1234 system, because all of them not going to have it. That really was an early engineering thing that they said, hey, we can let this, after we've already absorbed the heat in the evaporator and this cold refrigerant is going through here, we can let it absorb some of the heat from the liquid refrigerant so that it's even colder by the time it finally makes it to the evaporator. And so they felt like that would make the system work better. But like I say, you're not going to see an internal heat exchanger on every vehicle. Question 10, a variable displacement compressor shows poor performance at idle. All of these could be the cause except, all right, one, you could have a restricted condenser flow, is that true? Or cooling fan failure, maybe a malfunctioning internal compressor displacement valve, or a low refrigerant charge causing low suction pressure, or a faulty cycling switch on the accumulator. All right, this is not going to be a good answer here. It's the except answer because most all variable displacement compressors do not have a clutch cycling switch. Alright, we've been here 15 minutes. Hope you guys enjoyed this. Hope you got something out of it, and I hope you'll let me know what you think about it. Now, while I take my tools and go to work, I'll talk to you guys later on. See you next week, and I'll have another test for you that's different from this one.